welcome to the Introduction to Organic Chemistry video. What is organic chemistry? Organic chemistry is the study of carbon-based compounds. There are some inorganic carbon-based compounds, such as CO2, but most of the compounds that we talk about in reagents chemistry that are carbon-based are considered organic. This used to refer to living things, as the study of these compounds, many of these compounds we'll be talking about, are actually originally from living things. In order to be considered an organic compound, a compound must have carbon in it. Some important things to keep in mind about carbon is that it has 4 valence electrons. Its configuration is 2-4 in the periodic table. So that we have 4 valence bonding electrons, and this actually leaves places for carbon to form 4 covalent bonds by sharing electrons. We're going to begin our study of organic compounds by talking about the hydrocarbons. These are compounds with only hydrogen and carbon, no other elements in them. There are organic compounds that have other elements. We'll talk about them separately. When we talk about hydrocarbon molecules and the bonds that they have, there are 3 major categories. The alkanes, which have all single bonds. The alkenes, which have at least 1 double bond. And the alkynes, which have a triple bond. We consider single-bonded alkanes to be saturated molecules. Once we add what's called a multiple bond, which is a double or triple bond, we consider these to be unsaturated molecules. The definition of a saturated hydrocarbon is one that has all single bonds, whereas an unsaturated hydrocarbon has at least 1 double or triple bond. Now, I know we use the word saturated and unsaturated in our solutions unit in a slightly different way. So I do want to kind of draw your attention to where this name comes from. If we have a molecule that is an alkane, such as ethane, there should be 1 single bond between the 2 carbons, which allows each carbon to hold 3 more H's. This molecule's formula would be C2H6. However, if we were to have a multiple bond, such as a double carbon bond, each of these carbons can still only make 4 covalent bonds. So they're only going to be able to hold 2 hydrogens each. Oops. This molecule's formula is C2H4. The idea of unsaturation is a little bit different here, but the general concept means that we're not holding as many hydrogens per carbon as we'd expect to in a single bonded molecule. Once you throw a triple bond in that mix, you can only hold 1 extra hydrogen per carbon in this molecule. So you have much fewer numbers of hydrogens per carbon. Saturated hydrocarbons are the alkanes. The unsaturated hydrocarbons are the alkenes and the alkynes. A summary for you. Each carbon can make 4 bonds by sharing electrons. These are called covalent bonds. We can have single bonds formed by sharing 2 electrons, double, share 4 electrons or 2 electron pairs, And a triple bond shares a total of 6 electrons, or 3 pairs of electrons. Any bond between 2 carbon atoms is considered nonpolar. This is important. Carbon will also frequently bond with hydrogen, and those are slightly polar bonds. When we talk about properties, if we wanted to contrast, for example, water versus a typical hydrocarbon such as hexane, water, as we know, has a boiling point of 100 degrees Celsius. Hexane's is much lower at 68 degrees Celsius. This tells me that water has strong intermolecular forces and hexane has weak intermolecular forces. So why is that? When we look at these molecules, if we look at their bond polarity, the bond polarity that water has in its oxygen-hydrogen bonds, if we look at our electronegativity difference, it's 1.2. Now in our hydrocarbon molecule, our carbon-carbon bonds have an electronegativity difference of 0. That's a completely nonpolar bond. In our carbon-hydrogen bonds, we have a very small difference. That's only a very slightly polar bond. So there's much more even sharing of electrons in hydrogen in a hydrocarbon. Also, keep in mind, if we wanted to check molecular polarity, we would do chop-chop. Water is asymmetrical. This is a very polar molecule. Has much more negative charge focused around the oxygen and much more positive charge around the hydrogen. Whereas when we do chop-chop to hexane, this guy's very nonpolar, extremely symmetrical. So the molecular polarity in a water molecule is not just considered polar, it's actually considered very polar. Whereas we have a very nonpolar hexane molecule. The polarity of water is what gives it those very strong intermolecular forces. What's important to be able to do when you see a question that asks you to discuss in terms of intermolecular forces, if they are strong, are going to lead to higher boiling points, more likely to be a liquid at room temperature. If they are weak, they're going to lead to lower boiling points, more likely to have a gas at room temperature, something that is easier to vaporize. There are several different kinds of hydrocarbons. These saturated hydrocarbons they're all single bonds are known as the alkanes. If you take a moment and you look at table Q, you're going to see a general formula. This formula actually allows you, based on the number of carbons you have in a molecule, to predict how many hydrogens you would have in that alkane molecule. An important thing to understand about the alkanes is how their boiling points relate to their formulas. Boiling points for straight chain alkanes, and we'll talk about what that actually means to be straight chain, are increasing as we increase our number of carbons. Pentane is C5. When I calculate our number of H's, we'll do 2 times 5 plus 2, which will give us H12. For hexane, this is C6, and H, we're doing 2 times 6 plus 2, which is 14. Heptane is C7H16. Octane is C8H18. Nonane is C8H20. And decane is C10H22. As you can see in this, what we call homologous series of alkanes, each of these vary by 1 carbon and 2 hydrogens. And as we increase the number of carbons, we are increasing the boiling point. So our consecutive members are going to vary by 1 carbon and 2 hydrogens. Our boiling point is going to increase because our intermolecular forces are increasing as we increase the number of carbons in these molecules. All of these compounds have an -ane ending to their name. And keep in mind, alkanes are the only saturated hydrocarbons. A nice application to the different boiling points of members of the alkane series is the application of distillation. Distillation is a separation of a mixture into its components at a boiling point. We talk about distilled water a lot, but a very special application of distillation is distillation in the oil industry. I know this is a difficult graphic to see very clearly, but one of the things that's important on here is we have this extremely tall distillation tower. Up to the top of it, we have a much lower temperature, and down toward the bottom, we have a higher temperature. And at different places on that, in that distillation tower, we actually have different what we call fractions or types of petroleum products coming out. To give you an idea of what some of these are, and I'm going to keep this very brief, you don't need to know or write these down. For the top of the tower, or the top of the column where the temperature is lower, we're going to have things that tend to be natural gases, or gases, many of which we call natural gases. And those are smaller molecules with only 1 to 4 carbons. As we're increasing down the table and talking about the lower parts of the column where boiling points are much higher, where boiling point's much higher and temperature is much higher, this is where we get our much larger molecules. So our small molecules at the top are 1 to 4 carbons, or things that we use for things like heating, cooking, and making plastic. Gasoline is obviously what we're putting in our cars. We also have a lot of heavier fuels, such as aviation fuel, kerosene, oils, things like that, that are coming out in the next couple ranges. They're much larger molecules of up to 18 carbons. Heavy distillates include our oil, our lubricating oils, such as you would put in your car. When we finally get to the residuals on the bottom, that's when we're talking about things like actually Vaseline, things like the road oil and asphalt that we use in paving our roads. Again, I'm not going to answer any questions about these, but it is a very important application of the distillation. Distillation is a very important application in petroleum and the petroleum industry when we take natural crude oil, which has all these different alkanes in it, and we want to be able to separate them into their fractions. So distillation allows crude oil to be separated into different fractions. We would not be able to use it if the gasoline in our car had things like Vaseline mixed into it. To wrap up with the alkenes and the alkynes, the alkenes have to have at least one double bond in them. If you go to table Q, they have the formula CnH2n. If you compare this to the alkanes, which are CnH2n plus 2, you can clearly see that we're going to have fewer hydrogens per carbon atom. When we name these, their names end in -ene. If a hydrocarbon has at least one triple bond, it's known as an alkyne. Because of that triple bond, a lot of bonding space is taken up. So our general formula from table Q is now CnH2n minus 2. So the alkynes have much fewer hydrogens per carbon atom than the alkanes do. Both the alkenes and the alkynes are considered unsaturated because of this lower number of hydrogen per carbon molecule. Compare and contrast little wrap-up table. Summarize everything we learned. All of these molecules are made of hydrogen and carbon only because they are hydrocarbons. They're all covalently bonded, but specifically, Alkanes are going to have all single bonds, whereas in an alkene or alkyne, you will have one double or one triple bond. Your general formulas are available from Table Q. I apologize, the subscript did not work in the table. Remember, alkanes are considered saturated, while the alkenes and the alkynes are considered unsaturated.